week 6. So, as per usual style, I'll first look at the assignment problems and then look at some additional problems.
So instead of doing other things,
Right.
it would be good if you could explain through the lecture material so that
For which
we
week?
can 6 weeks,
For week
sixth
6?
week, 6 week material.
Ah,
Yes,
okay.
so
Would you
that we
want me to
will.
first explain? Would you want me to first go through the lecture material and then do the assignment problems, or the other way
Yeah,
around?
that would be good, I guess.
Okay.
So after
All right.
explaining the lecture material, we will spend maybe half an hour or 1 hour to solve the. I mean, to
Okay.
give the idea hints
Okay. Okay.
to tackle these problems.
Okay. I see. Uh, hmm. So which week we are in?
Do you have the material with you, sir? Now,
I'm trying to open that.
okay. Maybe you can take others participant opinion also. That is my suggestion.
Hmm.
Can take maybe other participants their opinion. Accordingly, we'll continue.
Right. Yeah. I mean, so we are deciding to first go briefly over the lecture material of week 6 before coming at the assignment problems. So I hope everyone is on board with this. Uh, if you have any suggestions, ideas, please feel free to express them. All right. I guess then we can do that. Um, okay. So in week 6, uh, interesting. Okay. So what I'll do over for week 6 is that I was looking at the lecture material for week 6, and I noticed that a lot of the material covered in week 6, the questions for the covered material appear in week 7. So week 7, a lot of the questions in week 7 assignment have lecture material covered in week 6. So what I'll do is I will try to because the lecture material for week 6 uh, seems to be quite extensive. It can end up taking quite a bit of time and may exceed the length of the session for today. So what I'll do is I will focus on the part of the lecture material of week 6 which is relevant to the assignment problems of week 6, and then for week 7 I may focus on the rest of the material for week 6, which is relevant to the assignments for week 7. So that's how I'm planning to do this. Otherwise, this can end up taking the whole length of the session. Seems to be quite large lecture material. Okay, so I'm going to. I hope the lecture material is available to everyone. I'm not going to read through the lecture material. I'm just going to. Uh, I'm just going to explain certain concepts relevant to that lecture material, and then and give you some hints about how to compute certain things. So some things may be theoretically defined. I'll try to explain how you can sort of strategy to how to
Also, it
compute
would
that
be
thing.
good if we can give some examples like
Okay,
to
I
solve
can
such kind
formulate
of.
some examples. Sure.
Yeah.
Yeah. Okay. So let's look at week 6 where let's quickly form like a summary of week 6. So let's turn it down. All right. So throughout week 5 and week 6, we have seen we have been basically studying the problem of conditioning, um, conditioning of a problem. Okay, so so in general, what this means theoretically is that you have uh, uh, like you basically, let's say you have an algorithm that solves a particular problem. So when I mean a problem, what you have is that you have a set of input data. So let's say your input data, I call it some xin, is drawn from some vector space. Okay, so this input data is drawn from some maybe some large dimensional vector space. This is possibly a large dimensional vector space. And you have an algorithm, let's call that A, that operates on this input data and produces some output data. And this also lies in some vector space, let's say. So essentially, our inputs are vector inputs and our outputs are vector outputs. Uh, right now, I'm not talking anything about the kind of algorithm or anything as such. Assume that this is a deterministic algorithm which acts on this input and produces an output. Now, the conditioning of a problem effectively means that what is the change we can expect, the relative change we can expect in the output, uh, relevant if we have a small relative change corresponding to, uh, in the input. So essentially, what it means is um, how is so. Let's say this x input, I change it to some uh, del xin, and the output change is del x out. Or let me, for the sake of simplicity, let's use x for input and y for output. So x plus del x is my change in input. This is change in input, and del sorry, and del y is the change in output. So what I want over here is how is del y by y, which is the relative change in output, related to del x by x. Okay. And there are many reasons to study this. And one of the reasons to study this is as follows. So uh, uh, we want the algorithm to be a stable algorithm. So what does stability mean? So let me just write it. Uh, uh, we This is like a more like a philosophical statement. We want uh, A to be a stable algorithm. And by that, what we mean is that if we have small changes, and what this means is that small changes uh, in input should correspond to uh, small changes in output. Okay, so And why do we want this? So let me just list down two reasons. Uh, the first reason is that whenever in any practical scenario you are dealing with a problem where you have some input data and you're producing some output data, it's very common that the data would come with noise. So let me just write it. Data uh, often comes with noise. So we want our algorithm to be stable to noise. Okay. And by noise, you essentially mean like small perturbations from the actual data. So you could have any kind of noise. For instance, if you work with statistical problems, then it's common to assume some kind of Gaussian noise added to the input data and so on. So data often comes with noise, and so you want the algorithm to be stable with respect to noise. And the second thing is this is very common in uh, in uh, in matrix computations is that uh, 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 this is basically what we will call floating point errors. Floating point errors in matrix uh, communications, in matrix computations, right? Um, yeah. So whenever you store a real number in a computer system, if it's a 32-bit computer system, if it's a 64-bit computer system, it doesn't matter. The real number may not be exactly represented. You will incur some kind of floating point error, and so the matrix that you're working with actually when it's stored inside the system, there is always some small errors that it encounters. So what you want is you don't want the algorithm to produce uh, uh, to have large differences in output when which is incurred because of these floating point errors. So in general, we want algorithms to be stable algorithms. This is not, I understand this is not really the thrust of this course, but if you're interested in working in problems in these numerical methods, designing approximation methods to for numerical computational problems, then it's very important to design stable algorithms. Okay, so having said that, uh, just give me 1 second. Right. So having said that, like the most basic problem that we can deal with is what we'll call a matrix uh, is a matrix uh, vector multiplication problem. Okay. So here we have as an input we have some x drawn from some Rn and uh, Rn, and we have a matrix A uh, which maps this n vector to an m dimensional vector. So it is an m cross n matrix, and we are looking at y which is equal to ax. Okay. So the input over here, just to be very clear, the input is x, which is in Rn, and the output is ax, basically.
Sorry, your voice is not
Okay.
audible.
Hello, am I audible? Uh, Not audible, is it? Can someone confirm that I'm audible? Hello, I'm audible. Am I audible?
Now you are audible, sir. I connected my headphones. If I removed it, I don't know it. You are not audible.
Okay, okay, okay. Okay, so in this matrix vector multiplication problem, the problem that we are going to deal with, uh, at least relevant to this, is when we are going to consider perturbations of x. Consider perturbations of x. So x is my input. So basically, I want to study uh, I want to study del y by y. Uh, how is it related to? Is it less than or equal to some constant times del x by x? So basically, what I want is, can I produce a bound like this? Okay. Uh, and I typically want this constant c to be a small constant. So this is uh, what we're going to study, and for any problem, uh, and for any problem uh, that we have described above, like this, uh, if we have del y by y to be less than or equal to some c times del x by x, then the smallest c for which this holds, roughly speaking, is known as the condition number of the problem. Okay. Um, of course, you have to give some bounds on how large you want this del x to be with respect to x. But if you assume that this del x by x is kind of small, then the uh, then this c is known as the condition number. The c is the smallest such c, which lets you write this inequality. Okay. So for this matrix vector multiplication problem, the condition number, which you'll obviously understand is dependent on a, is called ka, and it's called the condition number of the matrix. I won't go into how this condition number of the matrix is derived, but I'm just going to state the formula. You can look at the derivation in the notes. Uh, uh, but this ka is equal to the norm of this matrix A times the norm of the inverse of the matrix. Okay. Now, what is the norm? The norm is just the choice of norm you put on your vectors. So if it's the two norm, then it's the two norms. If it's the one norm, it's the one norm. So it's essentially the choice of norm that you have placed on the spaces. Um, the thing that you immediately notice is that there is an A inverse uh, uh, there is an A inverse norm term there, and so you may immediately ask, well, what happens if if A is not invertible, right? And the and so what happens is that when A is not invertible, then the condition number of the matrix, then basically this problem is ill posed. It's ill posed in the sense that the condition number blows up. It's actually infinity. And to see why it's actually equal to infinity, so let me actually write this. Okay. Um, all right. So uh, say say A is non-invertible. So it's basically a singular matrix. Then the condition number kappa of A blows up. Well, why does it blow up? can anyone state an explanation why if it's a singular matrix, why should the condition number blow up? Basically, it's not defined. If A is not invertible, this thing is not defined only. But I'm actually stating more than that. I'm saying that this kappa of A is basically infinity. Uh, like, can someone give an explanation why that should happen?
I think from the definition of norms only, sir.
Sorry, what?
If you use any norm,
Hello.
maybe a singular matrices for singular matrices,
Yeah.
determinant is, I mean, 0, and say inverse is not defined.
Yes.
So hence, maybe we can
No. 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 No.
say
No.
that in that type.
For a singular matrix, this is not zero. This is obviously not zero.
Norm is, I mean, norm different, sir. I'm determinant, I'm saying about determinant.
Norm is not zero.
Yeah,
For
norm
any
is
matrix,
non-zero.
recall that the definition of norm is sup uh, x equal to 1 x. This is the definition of the norm, right? Recall this definition. So, this is
Yeah.
equal to 0 if and only if A is identically equal to 0. So this is not equal to 0. But you can't say anything about this. This is just defined only uh, if it's a invertible
Non-singular.
matrix. Yeah. So let's see
Yeah,
why this is.
invertible.
Yeah. So let's actually see why, if A is non-invertible, why is this problem ill posed? So the thing is, if A is invertible, so then what happens is that the null space of A is fine. It has some positive dimension. So this is not equal to 0. Okay. So that means that you can find some V in the null space of A such that A times B is equal to 0. V is obviously not equal to 0. Okay. Now the problem is what happens if you try to study this conditioning problem with respect to this input del V, right? So so AV is equal to 0. Now consider a small perturbation of V. So consider some small vector. Uh, uh, so consider some small vector U. Uh, okay. U is a vector with a small norm. Then A times V plus U is equal to AU, right? Uh, but what is AV? AV is equal to 0. So so this uh, so if you just study this, so this C is greater than or equal to uh, del of AX upon AX uh, by del X uh, upon X, right? And so what happens is that you can choose U to be any small. So let me just write it. We can choose U to be any small vector such that AU is not equal to 0. Okay. Now then, if A is not equal to 0, obviously this quantity is not equal to 0 because this is U by B. Uh, and this del AX is equal to AU, but AX is equal to 0 because AX is just AV over here. So if in this case, what happens is that you write it in this way. This is AU uh, by AU by AV upon Q by, okay, uh, now this is equal to 0. And so this condition number is C is obviously infinity. And so what happens is that if you have a non-invertible matrix, the matrix vector multiplication problem is ill-posed. It's ill-posed. It is ill-posed specifically on the null space of A. So around the null space of A, this thing is going to be uh, uh, this thing is going to be uh, non. It's going to be imposed. But if you look at some other subspace where which is different from the null space of A, then possibly the matrix vector multiplication problem may not be imposed there. Okay. So what I would urge you to do is think upon think on like what are the subspaces in Rn, which is basically the input space. What are the subspaces there where this is ill-posed? So it's obviously ill-posed on the null space. So if you take the input to be on the null space and if you slightly perturb it, this condition number is going to blow up. So this is one reason why we have the problem is only well posed if this is equal to if this is a non-singular matrix, that is, it's a full rank matrix. Okay, so I hope this is clear. Now comes the problem, which is a slight variant of this, or maybe just the same thing, which is an equation solving problem. So let's say you are given a x equals b. You want to solve this. So just to state, x is a matrix is a vector in Rn, so is B, and A is the Rn cross Rn. Okay, and so if you want to solve this Ax equals to B, uh, uh, so your input over here, just to clarify, what is the input? The input over here is B, and the output is a solution x solve, where Ax solve is equal to B. Okay. Now, if you want to solve Ax equals to B, you'd immediately recognize that there are many ways to now solve it. You have seen the QR decomposition. The QR decomposition gives you one way to solve it, and of course there are many flavors of that QR decomposition. How to do it? Uh, uh, but let us look at the simplest way of solving it. Where the simplest way of solving it is just doing x equals to a inverse b. Okay, so what happens is that the problem of solving Ax equals to B just becomes equivalent to this matrix vector multiplication problem, where the input is B and the matrix that you are operating with is A inverse. And so the condition number of this problem, which is del x by x, uh, is actually equal to the condition number of A inverse times del B by B. And so the condition number of A and A inverse is just the same, obviously, which is this is just equal to the norm of A times the norm of A inverse. Okay, so this is one thing to keep in mind. A lot of solved problems would be solved with this strategy. Right. Okay. So one more equivalent expression for the condition number of the matrix. Um, right. So the condition number of the matrix has an equivalent expression. uh, okay. Um, so if you have an invertible matrix, if you have defined this quantity, it's called the norm of A, and this is defined as max of uh, x belonging to one Ax, right? You may as well define. So let's call it A capital M. You can also define something this like this. Let's call it A small m with a subscript, and this is equal to min of x belonging to one x. Okay. Now this quantity is going to be greater than zero if and only if A is non-invertible. Okay. Right. So if this is going to be greater than zero if A is non-invertible. I hope this is clear why that should be the case. Now, there is a relation between uh, am, a small m, and uh, uh, a inverse capital M. There is a relation, and the relation is like this. So, so this is just the reciprocal of this. Okay, and if you use this uh, uh, if you use this relation, then an equivalent way of expressing the condition number is equal to the max of this divided by the min of this. The advantage of using a notation like this or a relation like this is that it does not require you to compute the inverse of A. Although we will see that there is uh, 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 there is an analytical uh, description of uh, the the norm of A, which doesn't and the norm of A inverse, which doesn't require you to explicitly compute the inverse. Okay. Now, if you use this relation for Ka, it becomes kind of obvious why if A is non-invertible, if A is a singular matrix, why this kappa A should become infinity. Because if A is non-invertible, then this minimum quantity would become equal to zero, right? So this gives you a very obvious picture why this should be the case, right? Yeah, I hope it's clear. It also tells you one thing that uh, uh, that even if A is non invertible, sorry, if A is invertible, but if this quantity is small, which is this quantity, uh, if this is small, uh, or this is large, then again, uh, then again, kappa A is large. Okay. So uh, I guess uh, I guess it's still not evident what this should be. So let me just give you one idea. Uh, if so, what is this norm of A? Is the question. What is this quantity? So if A is a diagonalizable matrix, then this is equal to uh, the max of mod lambda, where lambda belongs to the spectrum of A. Okay, so spectrum of A means the set of eigenvalues of A, and the matrix norm, which is basically this quantity. Let me explicitly put this subscript. This is equal to the norm of the largest eigenvalue. Okay, uh, and uh, and the proof is actually quite simple to see why that should be the case. So notice that uh, um, if you have a matrix B, and if P is an orthonormal matrix, uh, then norm of PB is equal to the norm of B, right? And so what happens is that if actually I wrote diagonalizable matrix, I don't think this is the right term to use. I think uh, I feel this is not the right term to use. Let me just type it in this way. Right. If A permits a diagonalization of the form uh, uh, P transpose DP, where P is an orthogonal matrix, an orthonormal, where P is an orthogonal matrix, uh, then of course the norm of A is equal to the norm of D. D is a diagonalizable matrix, and for a diagonalizable matrix, the norm of D would be uh, the the uh, uh, the absolute value of the uh, of the eigenvalue or the entry inside that diagonal matrix, which has the large. So essentially, if D is equal to diag of lambda one comma up to lambda n, then the norm of D is equal to max uh, is equal to max of lambda. Okay. Uh, so in general, this is going to be true for symmetric matrices. Um, so uh, it's also going to be obviously true for. It's actually true for a larger class of matrices. You can ask when does A permit a diagonalization of this kind? It's true for a larger kind of matrices. Uh, essentially, essentially linear transforms which satisfy T star is equal to T star T. Uh, Such linear transforms always permit a diagonalization of this kind. Okay, so where T star is the adjoint of T. Okay, so yeah. That's uh, that's a criterion for saying when A permits a diagonalization of this. Now, okay. So one strategy that you can use to compute this A max, this norm of A, is to compute the largest eigenvalue of A. Basically, when I mean largest, I mean the largest eigenvalue with the largest absolute value, and that's going to be your norm of A. Now, the norm of A inverse. The thing is, A and A inverse, the eigenvalues of A inverse are just going to be the reciprocal of the eigenvalues of A, and so in order to compute A inverse norm of A inverse, you look at the smallest eigenvalue, and by mean smallest, I mean the one with the smallest absolute value, and you take the reciprocal of that. So that's going to be your norm of A inverse. So then what happens is that there is an equivalent way of writing this KA. You can write this KA. So let me just put a asterisk over here. Say for a symmetric matrix, you can write this KA as equal to the uh, the this part. Except only the fact that symmetric matrices always have positive eigenvalues. So this is just equal to lambda max by lambda min. Okay. So this is a formula that you can use to compute uh, this uh, this quantity. Yeah, hope it's clear. I hope you know how to compute eigenvalues. This is known. Right. Hmm. Just give me 1 second. Just give me 1 minute. I'll be back in a minute. Okay. Um, so, uh, okay. So, yeah, I hope this part is clear how you can compute this conditional number of A's. But in general, even if the matrix is not symmetric or not diagonalizable, this kappa of A is actually equal to the square root of the largest singular value of A. So, are you familiar with singular value decomposition of a matrix?
Yes, yes, sir. Yeah.
Okay, has it been covered in this course, or
No, actually, we have studied that concept for other purposes,
okay,
for teaching
okay, okay,
purposes.
okay. I see. Yeah, yeah. So, for those who are not familiar with singular value decomposition, you can have a look at the uh, singular value decomposition of a matrix. In general, what we can say is for a matrix A, the singular values of A are actually the eigenvalues of. So let me just write it down. The singular values of A are uh, the eigenvalues. Sorry, are the squares of the eigenvalues. Are the squares of the uh, no, I'm so sorry. It's not the squares. So the singular values of A are the square root of the eigenvalues of A transpose A. So even if A is not a symmetric matrix, A transpose A is always a symmetric matrix, and so you will always get positive eigenvalues of A transpose A. Okay. It's a real symmetric matrix, and because it's a positive, because so you can take square roots of them. So those are the singular values of A, and you can equivalently express these kappa of A in terms of the singular values of A. It's just going to be equal to the largest singular
I have one
value
question.
divided by the smallest singular value. Yeah. Go on.
Yeah, actually,
Hello.
singular values of A means eigenvalues of A into A transpose only. But can we define the same? Can we get the same singular values of A of the matrix A into A transpose?
Uh,
I mean,
A into A transpose
yes.
is
Yeah,
what you're
yeah,
saying. A times A transpose.
yeah, yeah, into
Does
A transpose.
A times A transpose and A have the same singular value?
Yes, yes.
Uh, uh, yes, I think yes. I think
Yeah,
that's true. Yeah,
yes, yes. Yeah. Okay, sir.
actually true. Yeah, yeah, you can do the same.
Okay, okay.
Okay, so hmm, right. So this is just this is like a. I mean, these are all computational stuff that I'm telling. Uh, in, in case this is not a symmetric matrix, you will have to resort to computing singular values. Okay. But generally, they'll give you such matrices where uh, the the operator norms can be figured out rather easily. They'll try to give you such questions for computation purposes. But for actual real value problems, in order to find the condition number for matrix, you'll have to resort to these kinds of expressions. Okay, um, fine. So there's one more thing. Yeah, so I stated here that this that uh, A small m, which is the minimum of x belonging to 1 ax. I said that this is equal to 1 upon this quantity. And uh, this is the in case you're interested, this is a small proof for that. Um, so let alpha equals this, and alpha prime equals this. Then uh, then obviously, if you look at uh, this map from this set to R, so consider this map which sends this to which sends x to uh, norm of ax. If you consider this map, then this map uh, will continuously take values from alpha to alpha dash. So basically, alpha is bigger than to alpha dash. So the range of this map is alpha comma alpha dash. This is the range of this map. Okay, so basically x goes to alpha comma alpha dash, and so alpha is the smallest uh, uh, is the minimum value of this function. So essentially, what this means is that there is a vector y. Uh, exists this vector y such that ax is equal to y and norm of y is equal to alpha. Okay. Now, now, so A is an invertible matrix, obviously here. So A inverse of y is equal to x. Okay. So now the claim is that uh, uh, A inverse. So if you look at this set, so the claim is that uh, if you look at this set, uh, uh, W is equal to alpha, W norm is equal to alpha, then max of W is equal to alpha, A inverse of W mod is equal to 1. This is the claim. And uh, the max is achieved at y. So y is some vector where the norm of y is equal to alpha. And what I'm claiming is that so you can think of a picture like this. Uh, let's say this is the radius 1 circle, and suppose this is the radius alpha circle, and there is some point x over here which comes to some point y over here, right? And what I'm claiming is that if you look at this entire circle, which is norm of w is equal to alpha, and if you apply A inverse of w, then you can only go as far as 1. You cannot go any further than that. And the reason is this, because uh, uh, so if uh, if this max is greater than 1, then that would imply, so let me just write it, if max of A inverse of w uh, if this is greater than 1, uh, then there exists some x prime uh, where norm of x prime is greater than 1, such that uh, such that norm of A x prime is equal to alpha, right? Yeah, so that norm of Ax prime is equal to alpha. But then what this means is that norm of A of x prime by x prime is equal to alpha by x prime mod. So this is a quantity which is smaller than alpha. So what this means is, so this contradicts the minimality of, so let me just write it down. This contradicts the minimality of, so this contradicts the minimality of this quantity. So, so what we have is max of, so max of alpha is equal to A inverse of W is equal to 1. Okay. Uh, this is for any W belonging to this circle of radius alpha. But what can you say about any uh, 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 but what can you say about this is not how the norm of A inverse is defined. The norm of A inverse is defined for such W's for which the norm is equal to 1. So it's pretty simple. So what you just do this. So that means that max of so it means that max of W by this times A inverse of W by alpha is equal to 1 by alpha. Okay. Now this quantity obviously is norm 1. It's a norm 1 quantity. And so you get max of W belonging to 1 times A inverse of W is equal to 1 by alpha. It's like a change of variables that I've done, except that, or let me just write it as W bar. But W bar is equal to W by alpha. Okay. And so what this gives us is that the norm of A inverse, which is this norm, is equal to 1 upon this guy, which is what we set out to prove over here. Uh, over here. So this is what we wanted to prove. So that, yeah, I did not find this derivation in the notes anywhere. So I decided to give a proof for this. Uh, that's why it's not there in the notes, at least what I saw. So, okay. So this is one proof of it. It's a simple proof. All right. So let's look at the last part of the notes, and that is related to computing least square values.
Sir, one more thing.
Yeah.
So before starting the least square concept, can
Yeah.
you quickly explain the concepts like if you put up X matrix, then how much error? I mean, what happens in the system? Similarly, if you put
Uh,
up the right hand side matrix B, then what is the relative error?
uh,
Those kinds, which are already there
oh,
in
okay.
the
Okay.
here, just briefly once.
No, I
Then,
already described it. No, that I was talking about the condition number. You know, are you not talking about this? Are you talking about something else? I'm not able to understand your question.
yeah, I mean, if suppose Ax equal to B is the given system,
Yeah,
so if you put up the right hand side system, right hand side vector B,
yeah.
then there is a relation between the relative error in X and the relative error in B.
Yes.
So similarly, if you perturb the given matrix, coefficient matrix A, there is a relation.
Yeah, that's a very good question. I don't think that's covered. That's part of the course. So
Yeah, yeah.
so that's
I am.
that's just part of the
Request
problem.
to please cover the whatever there in the content course. Then later on, if there isn't time, then please explain these other things.
Yeah. So I what I understand is this is what you're asking. So let's say we have ax equals b. Sorry. So we have the matrix vector multiplication problem, which is a and some input x. So we have x and we want to compute ax. So we have studied what happens if you perturb x to x plus del x. Now you of course have a question: what happens if I perturb a to a plus delta A, where delta A is some small perturbation. This is what you're asking, right?
Yes, 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 yes.
Yeah, yeah.
Similarly,
This is not. This is
vector B
not there.
also.
Yeah, yeah. I mean, so I mean, if you solve ax equals to b, that is just equivalent to solving for that is just equivalent to this operation, right? A inverse b. So solving this problem and solving this problem are equivalent problems. So
Yeah,
there are two parameters inside the problem. One is the input vector, and the other is the matrix. So you can consider perturbations of either the input vector or the perturbations of the matrix, or both. Generally, generally, so yeah, I mean, you can sort of do this. So you can do a plus del a x minus ax, uh, and that would be equal to delta A times x uh, upon ax. And you can ask what is the condition number of this problem. So let's call it like C, something like that, and C times uh, delta, yeah, C times delta A by A. You're basically asking this problem, right? Where A is getting perturbed. Um, right. And this is not there in your, at least this is not there in the course material. I have studied it before, but I can't remember it on top of my head. What is the this thing? It's a bit complicated. It's not as simple as the
so
it's
it's
not
already
as
there in
simple.
the material. Yeah,
Sorry.
it's there in the material.
No,
But
it's not there in the material.
yeah, if you simultaneously put up coefficient matrix and right hand side matrix, then there is a relation between relative index and this both perturbation matrices.
No, I'm not able to see it. Like which week is this? Week six?
Yeah, in week 6 is there.
Week six? Which page? Can you tell me?
I don't have that material at this moment. I think week 6. Yeah, the
Oh, okay, okay, okay.
before starting the least square.
Okay, okay, okay. I see, I see.
Yeah, yeah.
Right.
So in the next time, please
Uh,
show the material one, sir, and then explain the whatever the content covered in the material first. Then
okay, I will cover that in the next one. Let's say you don't have a question regarding that, which is the
yeah,
uh,
I don't have, but
yeah,
anyway, because sometimes we may busy with some other works, so we may miss some important points in that. Maybe it would be
yeah. I will do that next week. So next week during the session, I will look at this problem where the matrix A is getting put out. I'll look at that problem.
also no need.
I'll.
We understand
Huh?
it. I understand it. But next time
Mm-hmm.
onward, the week 7, please focus on the lecture material. Whatever faculty covered in that material, please discuss those things first, and then
Okay. Problem.
if there is any time, we can discuss maybe other things. The one which you proved just now, similar kind of things.
Yeah, I mean it's important to prove
Request,
everything. It's a
request.
theoretical course, so everything should be technically be proven unless something is really beyond. Unless something is really requires some outside concepts, then we may drop the proof. But otherwise, things should be proven more or less. Is
Yeah.
my understanding. But okay, I will discuss it next week. Uh,
Okay, sir. Okay. It's already 7:15. Maybe you can start least square briefly, and
yeah,
then we'll
okay.
maybe we'll
Yeah,
discuss the question.
I've looked at the questions for this week. They are not difficult. They're mostly computational problems, so we should be able to cover them relatively fast. Okay, so we'll do this next week. Uh, next week 7. Right. Finally, for the least squares, I'm not going to describe it absolutely extensively, but I'm going to look at um um just give me 1 second. Hmm, hmm, hmm. Okay, so so the least squares problem, you know how to solve it, right? In the sense that if you're given the vanilla problem where there's no weighted concept in it, so essentially you want to solve, you want to minimize this. You want to minimize ax minus b. Uh, this is the program that you want to minimize. And of course, there is a well-defined formula for this, which comes from taking derivatives, which is x equals to the pseudo inverse times b, right? So that would minimize this problem. But you may not necessarily have to go by this route. What I'm trying to say is there could be an easier way to solve it. You do not have to necessarily take the pseudo inverse. That can be computationally expensive. So the insight is a geometric insight basically. Uh, so what is so if we just write this down quickly enough, you have a vector b, right? And you have A. So what is A? A is some matrix A. Let me just quickly write down the dimensions. Let's say B is some vector in Rn, and A is some Rn cross n matrix. So A is a collection of uh, sorry. This is n cross n. So A is a collection of these column vectors, right? And you want to find out uh, and want to find out an x such that b minus a1 x1 uh, plus dot up to am xm is minimized. Okay, um, where x is obviously equal to um, x1. So, and these are vectors. These are basically the column vectors of A. Now this program, this is the case for the two norm, because the two norm basically comes from the inner product. So basically, the two norm of X uh, is coming from the inner product of X, right? Inner product in the Euclidean space. So that's why and it's a result uh, I mean, in general, it's a result in Hilbert space theory that for Hilbert spaces, the if you have a subspace, in this case, our subspace is this. So the subspace, I'm going to denote it by E. This thing. It is the space spanned by these vectors. So if you give me any vector B, then the distance from B to this subspace is going to be minimized at a point uh, B star belonging to A, such that uh, such that B minus B star is uh, is orthogonal to A. So that belongs to this guy. I mean, in the Euclidean space, it's easy to draw the picture. So let's say this is some hyperplane. This is A, and you are given some vector B over here. You basically draw, you project it normally. So let's say this is 0, uh, and this is your vector A. Sorry, let's say this is your vector B, and you project it onto this plane, and you have a point B star over here. So the minimum distance would be norm of B minus B star. So that's going to be the minimum distance. So what you have to do is you have to compute this point B star, which lies in this subspace A, which is perpendicular to. So basically, what you want is B minus B star to be perpendicular to this hyperplane, which is spanned by these vectors. Okay, yeah, I'm just going to write it like this. Okay, now this is now let me just state the problem this way. So uh, um, so this so let's say you write this hyperplane uh, denoted by this. So this is basically the span. Let me just be very clear what I mean by this. So this is the span of the columns of A. Okay, and this is a this is going to be a hyperplane. So let us find an orthogonal basis or an orthonormal basis for this thing. So let's say you have an orthonormal basis. You write the orthonormal basis as Q1, Q2 up to let's say Qm. Okay, or it's possible that I'm going to write this up to Qk, where k is less than or equal to m. So notice that even though A is a collection of these column vectors, which are the columns of A, the column vectors themselves need not be linearly independent. Okay, so this K is basically equal to the column rank of A. K is the column rank of A. Okay, and Q1 to Qk is a uh, uh, is an orthonormal basis of of uh, uh, the span of it. Okay. Now, then basically, you can easily show that this B star is equal to uh, the projection of B onto these elements. So that is just equal to B comma Q1 plus up to uh, B comma qk. Right. Uh, so if you do b minus b star uh, times any vector, if you take over here, you can do some qj. Uh, this is going to be equal to 0. Okay, so this is the B star vector that we are looking for. Now you can have a nice matrix representation for this quantity, and the matrix representation for this quantity is basically this. So let Q be the matrix given by Q1 up to Qk. Uh, so the matrix representation for this vector is basically Q times Q transpose B. And why this is equal to this, I leave it to you to convince yourself. Okay, so so B star is equal to Q times Q transpose B. Uh, and B minus B star is equal to uh, uh, I minus Q transpose times B. So basically, this is the matrix that we're essentially looking for. I minus QQ transpose, and that's not difficult to compute. So basically, the idea is that start uh, with the columns of A and compute uh, compute via the Gram-Schmidt uh, orthogonalization. You compute a basis Q of the span of the column surface. Okay, and once you have computed this basis, all you need to do is you need to do I minus QQ transpose times P. So this is what you are basically looking at. Yeah, I hope this is clear. Uh, you may have noticed a formula like this that shows up when uh, do something like um, when you do something like reflection. You would have seen reflectors studied in one of the previous courses. This is very similar to that. In fact, this is just exactly that only. Uh, but you need an orthogonal basis for A. So this is one equivalent formula the for computing this minimization program. Okay. The other is of course by standard differentiation route. This is more like a geometric approach. Okay. Right. So having said that, now let's look at the problems from this week. I hope the material is clear. And no, I basically said this because this may be computationally easier than going and then actually computing the speed inverse. Okay, so let's look at the problems for this week. We have about half an hour left. Okay, for which type of matrices is the condition number independent of the chosen norm? Okay, can anyone discuss this? Give the solution to the first problem. For which type of matrices is the condition number independent of the choice of norm?
I guess orthogonal.
Why is that?
Orthogonal matrix.
Is it? Um,
I'm
are you
thinking like
sure?
that. Yeah, yeah.
Okay, let's. Um, so for an orthogonal matrix, uh, what is the uh, uh, what is the uh,
Condition number is one
what is the
for all.
what is the condition number? The condition number is one. Okay,
Okay.
and so the condition number is one. Well, why is it equal to one? It's one only in the two norm, right? So let me just write it. Let a
We can use any norm, I
uh,
guess.
huh?
We can use any norms to get that one.
No, it's only true for the two norm.
Is it okay?
So let A be an orthogonal matrix.
Hmm.
Uh, so this means that A is an orthogonal matrix. Then the of course the two norm is equal to one, right? But what is A uh, in the infinity norm? What is this? Well, this is equal to. So if you
Actually, we are
write, uh,
condition number is about the product of norm A and the norm
yes,
A inverse.
yes.
So if it is
So
simplification, then
so
we
that
may get the
so
result.
kappa of no no so kappa of A with respect to the infinity norm is equal to this, right?
Yeah, yeah, yeah.
Right. So what is this? So this is equal to A infinity times A transpose infinity, right?
Yeah.
Correct? Because A inverse is equal to A transpose. Now what
Yes.
is
Yes.
A infinity norm for a matrix? We discussed this last week. The infinity
Yeah.
norm for a matrix is yes
Maximum
is
absolute rank.
basically look no not it's basically no it's not that you look at the rows of the matrix A and you
Yeah.
figure out
What I'm-
which row has the you look at the sum of the absolute values of the entries of each row and the row which has the for which this is maximum, that is the infinity
no,
norm of this thing, right?
that's what
So
I'm saying.
this is for
Maximum.
A.
Okay. Yeah.
I Aij, right? So this is essentially the columns and rows are have been transposed. So this is the maximum sum, this maximum sum of absolute values of the two columns. You cannot guarantee the product of that two of those two would be equal to one. How can you guarantee that it's always going to be equal to one? Are you getting my point?
Yeah, but I don't know. Maybe symmetric matrices
Yeah,
also.
what you can do is you can actually hand construct a a wait, just give me 1 second. You can actually hand construct a an orthogonal matrix. So you can do this. You can do cos theta, sin theta, minus sin theta. Right? You can do this. No, this is an orthogonal matrix. Let's say A is equal to this. Then the norm of A is equal to uh, cos theta, absolute value of cos theta plus absolute value of sin theta, right? And this is also equal to cos theta plus sin theta. Now, if you take cos theta plus sin theta mod and do a square of that, which is equal to A times A transpose, is it equal to 1 for all theta? No, right? I hope it's clear. This is a counter example.
Okay, okay, yeah, yeah. Maybe I haven't looked at it, but I'm guessing like, but haven't tried due
Yeah,
to
yeah.
some.
The answer is none of the above. Yeah.
Uh,
Okay.
is there any
Yeah, I mean
like?
you can use it.
Uh, I think maybe what about diagonal matrices?
No, but diagonal matrix is not there in the option though. Yeah, but if you have a diagonal
I'm
matrix,
looking at.
um,
Yeah,
then
diagonal
the
matrices. It is true, I
yeah,
guess.
I guess for diagonal matrices is true. Yeah, yeah, I think you're right. Yeah.
Similarly,
Um,
I haven't tried, but yeah,
okay, yeah. For diagonal
yeah.
matrices, this is probably going to be
I'm
true.
just guessing only. Yes, because I'm tried due to some other works. Yeah.
Oh, yeah, okay, sure. Yeah, the second problem is about the condition number of A if the matrix is singular. So we discussed it already in today's discussion before this. So you know the answer to that. Uh, let's look at the other problems quickly. Okay. Question number 3 and question number 4. What is the condition number of D in the infinity norm? We discussed what how to get the infinity norm. So we know how to do this, and the condition number of D in the two norms. Again, we discussed this elaborately in today's uh, uh, discussion, so we know how to get the condition number of D for this two norm. In particular, the eigenvalues of a diagonal matrix can be read off from the entries in the diagonal matrix. So we know how to do this. Okay, so 3 and 4 are done. Let's look at the other problems. Yeah, for the fifth problem, uh, Yeah, this is just a definition of the condition number. Definition of condition number.
This
Okay.
portion is already covered in the lecture, I guess.
Yeah, this has been covered only before. Yeah, that's the thing. Yeah. Okay, let's look at this problem. Okay. So uh, this is well. I mean, this is basically the least squares problem, but given in disguise, this is the least squares problem. So, what is the Frobenius norm? So, recall if you have any matrix C's, uh, then the Frobenius norm of C is equal to sum over of Cij squared, I comma j, right? Now, you can of course write this Frobenius norm in a different way, which is if you take C and if you write C as this, uh, so let's say C is an R n cross M matrix. So there are m columns, and these are the column vectors of C. Then you can write the Frobenius norm of C as basically equal to the sum. This is squared, obviously, is equal to the sum of the two norms of these individual column vectors, right? So it is basically the sum of the two norms, the sum of the square of the two norms of the individual column vectors of C. Okay. Now, how is this related to this current problem? We have to find uh, uh, an x which is uh, x1, x2, x3, such that uh, a x1. Okay. Oh, okay. So b is given to us. It's given to us. It's b1, b2, b3. B1, B2, B3 are just these guys. And let's say you compute AX1, AX2, AX3. Okay, these are column vectors. These are not scalars. Just to be clear. So by the definition of the Frobenius norm, what you want is you want. Let me just write it. We want vectors uh, x1, x2, and x3, which basically live in R2 and which satisfy this quantity. So b1 minus a x1 norm squared plus b2 minus a x2 norm squared plus b3 minus a x3 norm squared is minimized. Okay, so what you have to do is you have to solve the least squares problem. So let me just write it. Solve the least squares problem for B1, B2, and B3, where B1, B2, B3 are the columns of B. So you have to take this vector, this vector, this vector, and this vector, and solve the least squares problem. And then you have to plug in the value, and the sum of this is going to be the square of this quantity. Okay. So yeah, so essentially you have to compute that x, which minimizes this once for b1, once for b2, and once for b3. So essentially, just to give like a closed form expression, each xi is going to be equal to this pseudo inverse of A times BI. You can either do the pseudo inverse, or you can just do by the projection formula that I just showed. In this case, you have a simple matrix A, so it's very easy to get an orthogonal basis of A. Okay, so I hope it's clear how to solve the problem. I'm not actually solving the problem. I leave it to you to actually get the exact answer. I guess. All right. Yeah, so understand that the Frobenius norm can be basically the key is to understand that the Frobenius norm can be written uh, as the sum of the squares of the two norms of the columns of the matrix. Okay, let's look at the seventh problem. Yeah, this is a very simple problem. Uh, yeah, this is the upper bound is just equal to the condition number of A. So yeah, this is just a form definition. Okay. The condition of number of an orthogonal matrix in the induced two norm is, well, we have discussed this multiple times, so we know what it is. Okay. The ninth problem. Which of the following statements are false? An ill-conditioned matrix is highly sensitive to small perturbations. An ill-conditioned matrix has a large conditional number. An ill-conditioned matrix is defined as a matrix with condition number of 1. The condition number of a matrix in the induced two norm is defined as the ratio of the largest single value of the matrix to the smallest singular value. Yeah, I mean, well, this. They are actually spelling out the formula, but it's not there in the notes. So we discussed this already in our discussion previous to this. Uh, it's clear which of the following statements is false, right? You know this statement is true because we discussed it just now. Uh, and the rest of the statements you can obviously uh, say which of them is false. Okay, let's look at the final problem. Um, so here they're basically asking you to give a lower bound on the condition number of A. So well, you know that uh, so if you solve this Ax equals B, then del B by B is upper bounded by the conditional number of A times del X by, okay. So the condition number of A is upper bound is lower bounded by uh, del B by B divided by del X on X. And so you can compute these del X's and del B's and plug in the values and Yeah, and you can understand. You can get the lower bound of the condition number. Just be careful. They're asking you to use the infinity norm. So appropriately use the infinity norm in this case. All the norms are infinity norms. Yeah. So the problems are relatively simple for this week. Yeah. So that brings us to the end of all the assignment problems. We are near the end of our time. If you have any questions, you can ask me. Otherwise, I'll close the session for this week.
The last question, I think they perturb the
Yeah.
right hand side vector.
Yes.
So that
No. The last question is basically this. The last question is, yeah, that's true. In the last question, they have perturbed the right hand side vector, and by perturbing the right hand side vector, the solution vector also got perturbed.
perturb, yes,
So
yes.
just to
The
yeah,
relation may
so
change.
yeah. So
Whatever
let me just write it. A perturb. Just quickly write it.
means
Perturbing B leads to uh, perturbing the solution X solved. Leads to perturbing the solution X solved. And so what is given to you over here is so if this is B and after perturbing it you call this B plus del B, then and if this was the solution X solved, after perturbing this is X solved plus some delta X. Okay. Now, of course, this is known to us. This is the definition of the condition matrix, um, and so you have an upper bound on the condition matrix by using this. So
around, I mean, relative error x is smaller than conditional relativity.
yeah, the relative error is smaller than condition number. Yes. So you over here you don't know the condition number. You're trying to estimate the condition number. Okay. You are trying to estimate the
Yeah, yeah.
condition number. So this is like this basically, as if you are given an oracle A. Do you know what is the meaning of the term oracle? An oracle is this is kind of used in computer science. So it's like you are given a machine. So an oracle means that you are given a machine where if you feed some input, it is going to give you an output. Okay. So in this case, assume that the matrix A is like an oracle. Okay. So if you feed in B, it will solve Ax equals to B and give you X. But you don't know A. Let's say you don't know A. But you have access to this oracle. So you can feed in as many B's and you can get the corresponding solutions. But you don't have A. So now, if you're given an oracle like this, the question is: can you understand? Can you can you get a bound on the condition number of the matrix A? So this is the kind of setup or framework for this question. And the you can get a lower bound. You can't get an upper bound. You can get a lower bound. uh, you can say that okay, this is the condition number of the matrix. So what you do is that it's like you are playing a game. So first you feed in B and you got X solved. Next time you see okay, I'm going to feed in B plus del B and I'm going to see what is the solution that I'm going to get. So you get X solved plus del X. So this kind of again the thing with this assignment problems is that the motivations of the problem being given is not often very clear. But if you're doing something like if you have like a cryptographic system, okay, if you have a system uh, that I mean, I don't know if you're too familiar with this with this side of argument, but let's say let's say there's a system that solves equations X equals to B. Now you don't know what is the algorithm it uses to solve this system. Okay, because the algorithm is not given out to you. Let's say the source code of the algorithm is something you don't know. Okay, the source code of the algorithm is with the person who gave you the package. Okay, What you can only do is you can give in inputs and you can get outputs. The source code is not with you. Now, if you are an adversary, let's say you are a hacker, and you want to understand, is the system stable? This is what you understand. You want to figure that out. And if the system, what you can do is you can you can perturb the solution, you can perturb the input a little bit, and you can study the perturbed output. Okay, by doing that, you can get an upper bound on the condition number of the algorithm. So, so then what you can do is that if you're a hacker, you have a way to potentially damage the system. If you can somehow tell, oh, the algorithm that he's using is not a stable algorithm, it's an unstable algorithm, then what you can do is maybe you can design an attack on that system. Okay, so this is more like a cryptography side of things. I don't have to be too much bothered about it, but yeah, you can get a uh, lower bound on the condition number. So, for instance, if this quantity is very large, then you can say, oh, that the algorithm that they're using to compute this output is not a stable algorithm. Okay. Uh, yeah. So that is kind of a motivation for
But,
doing something like
as for the lecture material, what are the B? There
that. Mhm. Sorry, I can't hear you.
more than
Hello.
conditional number times relative error will be.
Yes. Yes.
Yeah, yeah. As per the
Yes.
lecture materials,
Yeah.
uh, it is that inequality is changes. So that means relative error in X is smaller than the kappa times relative error in B.
Haha. Yeah.
So
Yeah.
we
Yeah.
have the proof.
Actually, yeah. Yeah. That's actually true. Yeah. Yeah. I think I made a mistake over here. Yeah, yeah, yeah.
Yeah,
Actually, I
that's
made a
what.
mistake. It should be del x by x. Yeah, yeah, yeah. Mhm. Yeah, yeah. Right, right, right. Yeah,
Yeah, no issues. No issues.
yeah. I'm kind of switching between the matrix multiplication problem and the solution problem, so that's why
Yeah,
doing this.
it's
But
okay, sir.
yeah,
And
yeah,
sir, I
yeah.
mean,
Thanks for pointing out.
is
Yeah,
this
yeah.
today? Yeah, yeah.
Go on. Yeah.
I think if possible, maybe conduct this meeting every Friday so that we'll all free on Friday. Because during
Yeah, yeah,
weekdays,
yeah.
we may busy with some.
Yeah, yeah. I was traveling last Friday. I had to meet a group, so I had a conference, so that's why I did not I could not be present on Friday or last Friday. Yeah, this Friday I'll be present. Yeah,
Good evening,
Mostly,
sir.
please try to. Yeah, yeah.
Hello. Am I audible,
yeah,
sir?
yeah. Please, yes,
Sir, last week, today also I joined almost 45 minutes late. Are you posting this video into that problem solving session links, sir?
yes, yes.
Actually, last week video is not available. That's why I'm asking this one, fifth week.
Oh, just give me 1 second.
Uh,
Uh, just give me
this
one
video
second.
is
I
private,
have
like that
uploaded
I
it.
got it. Video unavailable. It is private, like that it is showing.
Oh, okay, okay. It's somehow it has become a private video. Okay, okay. I'll make it a public video. I'm not sure how. Uh, oh, okay. Mhm. Okay, I'll make it a public video. Sure. So
Okay. Sir,
when setting the access of the video, it somehow it got selected to private. Okay, yeah, I'll make it a public video.
okay, okay. Can I expect this video by tomorrow, sir?
I'll upload it by today only. So no.
Okay, thank you. Thank you, sir.
Okay, I guess we're out of time, so we'll stop here. Okay, thank you everyone for joining.